We are going live. We should be live now.
All right. Welcome, everybody, to the April 8th version of our professional development seminar here at the College of Engineering at UAA. Today, we have a special treat for you. We are talking about ice crushing forces at the Port of Alaska here in Anchorage. Our presenter today is Jasmine Langman. She is a Masters of Science student, one of our actually rare Masters of Science candidates who is also a fast track student doing research. Jasmine completed her bachelor's in civil engineering here at UAA a year ago in the spring of 2021 and is now getting close to completing her master's here at UAA. So yeah, and so if you have not joined us before with a professional development seminar, there is a short quiz at the end, or there's a short quiz, I guess, posted on our website, and there's a password required for that quiz where you just, I believe you just enter the password and then you can enter your information to get your PDH certificate. So it is good for 1 hour of professional development. And so I will give the password at the end of today's talk, and then you can get your PDH certificates. Besides that, feel free to enter questions in the chat on the live stream, and we will answer those questions at the end. So, all right. So with that, and I guess I should also say that you know, it is very rare for me to get to introduce my own student. So this is kind of a cool professional development seminar. So with that, I will turn it over to Jasmine, and she will talk about ice.
Hello, everyone. My name is Jasmine, and thank you for coming today. I'll be talking about my thesis work with Dr. Hamill, which is co-investigated with Dr. John Zufel and Dr. Joseph Lakes. This project is funded by ConocoPhillips Alaska and with the support of Port of Alaska in Anchorage. All right. Okay, so this is my outline for today. I'll go ahead and introduce the project and talk about the purpose. And then the project and my thesis is broken into 3 parts. So the first part is the development of an ice core drill and procedure. So we did field extraction at the Port of Anchorage. Then we developed an ice core drill, and then I'll talk about some of our lessons learned. And then the second part of the project is our compression and shear testing. So we developed compression and shear testing apparatuses and a little bit of methods, and then I'll talk about the results. Finally, I'll talk about our 2D FEA modeling, finite element analysis, that I'm doing in Abacus right now. So there's compression components. I'm doing 3 models, a compression model, a shear model, and then I'm going to combine them into a ice pile interaction model. So basically exactly what is happening at the port, and then I'll be talking about the next steps. All right, so the introduction. So Anchorage has an average tidal range of about 25 feet. The Port of Anchorage has a lot of piles and is currently undergoing expansion. And every time the tide goes up and down, a new layer in the winter, a new layer of ice is formed. So depending on the temperatures during the winter, the accreted ice can be 3 feet in diameter or 10 feet in diameter. 10 feet is a little bit closer to what you see in the pictures on the right. The picture on the far right is from the 1960s. And if I understand correctly now, they actually have fenders so that there's not as much ice accretion, and ships aren't going to be impacting the piles. So the Port of Alaska is a linchpin in the state's economic vitality, and as I've said, it's already undergoing expansion. The piles must support impact of sea ice. So right now, there's been quite a bit of research into the strength of the sea ice or the ice flows, but there's not a lot of information on the width and growth and strength of the accreted ice on the piles. So because of this, designers have to make conservative assumptions about the size, shape, and strength of the ice attached to the structure, which increases project cost when you have to build or design and pay for hundreds or thousands of piles. So what's the problem? So the left picture shows an ice sheet hitting a pile and the pile breaking that. And that's what you want. You want the pile to break the ice and not the other way around. So there's crushing on the front and you can kind of see the debris following around the sides of the pile. And then there's shear forces on the side. And I'll talk a little bit more about that in a minute. The bottom right shows that ice can be very impactful and damaging to shorelines, and you don't want that on a structure that's like the port. This table shows the vessel and structure damage in Cook Inlet caused by floating ice. So these are some of the bigger damages that the Port of Anchorage and Anchorage City Dock has experienced. So most of it's caused by winter ice and tides, like those ice flows. So there's some situations where just ice. So like the second one, dock expansion torn from pilings and demolished, caused $1.9 million in damage. Other times the ice flows pushed one of the ships into the port. Or like the last one, there's damage to fender pilings. So this is a problem, and we need to address it, especially with northern expansion, with the Northwest Passage and the known port being built and other things like that. So in Cook Inlet, there's the ice flows or ice pancakes. I'll also might refer to them as sheet ice. The ice flows in Cook Inlet can be up to 500 feet wide or 750 feet wide. So they're pretty significant. Yeah. So what is the problem? So the blue on the bottom is your ice flow, and it's going toward the pile. And if you have a clean pile with no ice, this is kind of the setup image. So the ice is going toward the pile. And as you can see with the icy pile, the diameter is 3 times as wide. So when that ice hits the pile on the clean pile has to withstand like basically 1 diameter's width of the force, right? But with an icy pile where it's 3 times the width, 3 times the diameter, it has to withstand 3 times the amount of force, and the pile has to take that force. And basically you just have to design the piles to be a lot stronger, which, as I said before, costs a lot more money. And there's a big difference, you know, whether you have a clean pile or a 3-foot diameter ice or accreted ice or 10 feet wide of accreted ice. It makes a big difference. All right, so is the current design approach too conservative? So if the sheet ice, so if your ice is hitting, I'll go back a second. So if your ice is hitting the front, where the red is basically is compression. And then especially right in front of the pile. And then on the sides here, there's shear forces. So shear is like moving past each other, right? So the sheet ice is pushing this way and the pile is resisting. So there's shear forces on the side and compression on the front. And this slide is talking about if the sheet ice compression is stronger than the accreted ice shear. So if the sheet ice pushing through is stronger than the accreted ice shear strength, then the accreted ice breaks, which is shown in this image here. And then this means that the pile diameter is crushing the sheet ice. But the other scenario is if the sheet ice compression is weaker than the accreted ice shear. So basically the accreted ice is stronger than the sheet ice, then the sheet ice breaks. And the accreted ice diameter triples in this situation because it's staying intact. And then that's the current design approach. So it's very conservative. You're accounting for 3 times the amount of width or 3 times the diameter when you're determining your required strength of the pile versus just 1 diameter strength. Yeah. Okay, so our research goals were to characterize the buildup of the ice, so the strength of the accreted ice, the stiffness, and then we also looked at some other things like salinity and the amount of sediment in the ice. And then we're also going to be trying to predict the loads on piles for the new construction, and we're using a bit of modeling and calculations to do that. So these are kind of the existing conditions. This is what the Port of Anchorage, Alaska looks like now. So your main flow just goes right past because there's a point up to the top right. And then there's a bit of an eddy in front of the port, which when we were doing ice harvesting on site, I was kind of watching that, and there's a significant difference in the velocity of the tide out here, you know, when it's full velocity versus right in front of the port where it's a little bit slower. So the velocity kind of in the eddy is 1.6 knots, which is about 2 miles an hour, which is a lot less than the velocity of the water in the main channel. And then toward the bottom of the port is where the expansion is going to be. And that's what this looks like. So this is the south end of the port on the left. And then the new expansion is going to be out even more. And so this highlighted section here is more in line with the main channel tide. And so that's probably going to have more impacts than the rest of the new port. So, you know, knowing how strong the piles need to be in the ice and whether it can withstand the ice flows is very relevant to this project. All right, so I wasn't around for the 2020 section, but this is the method that, or the ice harvesting that happened in 2020. So we developed this ice core drill, basically a cylinder with a hole saw on the end, and we attempted to get cylinders right out of the created ice directly. The main problem with this was that there was no way for the ice chips to get out. And so the core would go in a couple inches and then get stuck. And yeah, we couldn't get a clean sample. Also, the outside layers of the accreted ice are a lot more aerated and kind of fall apart more easily than the interior layers. So we tried a couple different things. We used a chainsaw to cut out small cubes, about 1 by 1 by 1 foot cubes, and then drill those. And we did that like walking down the at low tide to get those samples. And then that's drawn for scale. So those ice piles and accreted ice are pretty big. And then on the right, we used a bucket lift, but we were it only went down far enough to get some of the top section ice. So we came back in 2020 with Greatland Tree Service, and they were tied off and rappelled down and cut out some chunks of ice that were about 2 feet by 2 feet by 2 feet. As you can see on the right, they put in ice screws into the ice chunks and then cut them out and hauled them up. And there's 2 people on the lower section on the left, below the deck on the left. So you can totally see the scale of the ice. This was in March, about mid-March of 2021. So pretty impressive. It was really cool to see that. Here's some more pictures. On the left, you can see there's 2 piles with basically a wall of ice in between, which was really cool. So we cut out a chunk there and tested that ice to see if it varied from the ice that was like closer to the pile. And then the picture on the bottom was us measuring the samples, the ice chunks, and we also labeled them so we knew like which side was the front side and the top side. So when we went to cut out our specimens, we knew exactly which direction they were, and I'll talk about why that's important in a minute. So this was really cool, the ice variation. So in the fall, there's more sediment moving around because there's more flowing water versus in the winter when there's more ice and all the sediment has kind of settled a little bit more into the ice. So the layer, you can kind of tell where the inside, if you're looking at it radially, which side, where the inside layers, the first layers, are the layers that froze in the fall versus the layers that froze in the spring. So the darker layers, like for this bottom one, the outside is at the top and it's a lot lighter than the more sediment section. And then you can see at the bottom, and then there's a lot more layers. You can see the individual layers in these other blocks. And then the two circles on the bottom left, that was from a radial cylinder where we cut off the ends to make them square. And that one side, one end of it was, you know, a little bit of sediment, and the other end of the cylinder had pretty like big pockets of sediment. So that was kind of cool to look at. All right, so this is our coring hole saw, which I have right here. So basically we took a hole saw and we cut off the blade, and then we basically just attached it to this 8-inch long steel pipe or steel tube. So we matched the hole saw exterior diameter so that there's a clean, so that it's smooth on the outside. And then the inside has a blade. So it's got two blades, one on the outside, one on the inside. So there's a little bit of a space on the inside. And then those were machine cut and tack welded in. And then at this end, we have like a plate attached to a chuck. So we can put this on a drill. Yeah, so we have two blades on the cutting edge, and it's about 8 inches long and 2 3/4 inches diameter for the ice cores. The outside diameter is about 3 inches. So we fabricated this ourselves. So it was about 12 inches of round tube. This piece was originally 3.5 inches diameter and 3/8 inches thick. And then Corbin, our machinist, machined it down so it was as true as possible, as round as possible on the inside and outside. We did do a second iteration of this, but with a thinner tube, but it was a little bit warped, so it didn't work as well. And then we have a 3-inch hole saw and a 2 7/8 inch hole saw. And then I included the machinist labor in our cost estimate. So it's about $437. It's pretty good compared to, you know, the $5,000 commercial versions that you see. All right, so this is our development of our method for the hole saw. So on the left, you can see Haley drilling one of our practice blocks with just the hole saw. And kind of like what I talked about earlier, there was no place for the ice chips that were getting cut to go. So we ended up drilling basically exit holes. So we have this red little template here, and we would screw it into the ice just with short screws. We ended up changing that, but we would screw it into the ice and then drill out the small holes with a drill bit, and then go in with the hole saw. So there was a jig required, and then the drill bit we used was 3/4 inch diameter and 12 inches long. So this is our steel template or jig. So we have a 6x6 steel plate, and then all 3 holes are on the same radius. So which was about 3 inches, which was 3 inches. So the 3/4 inch diameter exit holes, and then the 3-inch core hole. So we had a template on the drill, and then we would just switch out the tools and rotate it, which worked really well. So yeah, consistent radius between the rod to exit holes and the rod to core. So that allowed easy drilling. And this is a cost breakdown of this. So we have our steel pieces, which was about $40. The drill bit was $75, and the labor was about $300, so $400. All right, so this was our method. So the ice blocks, we had those big 2 by 2 feet ice blocks, and then we would cut them down into smaller blocks that were about 8 inches tall, so we could just slide them into this wooden template. So the wooden pieces were fixed except for the triangular piece, or the L on the front, that was movable, so we could just clamp the ice blocks into this fixed template. And then the blocks, yeah, the ice blocks were 8 inches tall, and then the minimum diameter to hold the block into place was about 5 by 5 inches on the looking from the top. So that the wooden stand had 2x4s underneath, and some holes under where the exit holes would be drilled, so that once the exit holes were drilled, ice chunks or shavings could fall through and it wouldn't get clogged. And I'll show you a video in a second, but we had to clear them out pretty frequently, but it worked pretty well. Yeah, so you can see that the template, which was the steel template, which was originally just drilling directly into the ice, we ended up drilling it into the template, so we didn't have to move it, and we only had to move the ice and the drill. Yeah, so step 1, drilling out the exit holes, and step 2, drilling out the core. All right, so ice core specimens. So if we're looking at the top view, which is the upper right, so we got our black steel pile and our blue accreted ice, and we wanted to know whether the compression strength was different in different directions. So whether it was strongest in the radial direction, the transverse direction, which is the yellow, the radial direction is the orange, or in the vertical direction, which is the green. Typo there. And then this is a view from the front. So if you're looking at the pile, your radial cylinder is going straight in, transverse is still from the side, and your vertical pile is coming from the top or bottom. And then when we were at the port, we noted like where the sample was coming from. Was it from the top of the pile, the middle of the pile, or the bottom of the pile, like what elevation? And then we also noted the amount of sun exposure. So some of the samples were on the south side of the pile, so they got a lot of sun, and some of the samples were on the north side of the pile, so they didn't get a lot of sun. And then once we got back to the lab, we melted this. Once the samples were tested, we melted them down and determined the salinity in the total suspended solids, which is basically just like how much sediment there is in it. Because as you can see from the specimen pictures, some of them had a lot more sediment than others. The other thing we considered was the depth or the distance from the pile. So if you got your black pile, and let's say the blocks were 2 feet thick, so we could have basically two radial cylinders, one toward the inside of the pile and one toward the outside of the pile, or the ice block. And we looked at whether the ice was stronger closer to the pile or farther away from the pile. Okay, so for all of our specimens, all the blocks were a little bit different size. So to get the most bang for your buck, or the most samples out of your block, I drew up these block cut plans for every block. So if you look at the middle bottom one, so that's the front, and I would cut out a shear block, and then I would get multiple shear beam samples from that. And then I would basically try to figure out how to get all 3 directional cylinders in the block, from the block. So I would have some radial cylinders on the front, and then some radial cylinders on the back if I could, some vertical cylinders, and then some transverse cylinders. So it took a little bit of time to wrap my head around, 3D thinking like that, but it was kind of cool because toward the end I was able to, whip that out in 5 minutes, when at the beginning it took me half an hour. So that was kind of cool. And that's why the orientation of the block was super important when we pulled it out of the port. So we had the front face, it was pretty obvious because it was the most crumbly and had a ice screw hole in it, but then the top and the sides was a little bit harder to figure out. So we made sure to pay attention to that. So this is some marks that we made for cutting the cylinder. So the red lines in the cut plan are where we did those big cuts. And then that's where the thin lines on the second picture are. And then we would cut it so it was 8 inches tall, and then we could just slip it into the template and drill the cylinders. And then on the right is Dr. Hamill using the chainsaw to level one of the practice blocks so we could fit it in the template and see how it did. All right, so this is a picture of our ice core drill and template. So we have our wooden platform and then our free moving piece here at the bottom. We ratchet strapped it in, and then our template was fixed in the wood. We had you can see there's a previous ice core that was drilled out of this piece, and then it was cut down so it was square and could hold. All right, so I'm gonna stop share really quick and try to share the video. Please let me know if there's any issues. So this is one of our poured ice pieces. Oh, this is the end of the video. There we go. So you can see there's a layer of sediment at the top and the bottom, and then it's strapped in. And then this is our exit hole, our shaving exit hole right there. And this is Keelan drilling these. She drilled a lot of these for me over the summer, so she's pretty good. But yeah, so you can just see the shavings are coming out of the exit hole. And if there wasn't, if the ice wasn't cut down that much, if it was a bigger piece of ice, the shavings would just go straight down the hole. And then the other hole got kind of backed up and wasn't excavating the shavings, so she just put the drill bit down there to clear it out, and then went again. And this is kind of when she hits that second layer of sediment, and it's slowed down a lot. The video actually goes on for like 2 minutes while she tries to get through that next layer, so it takes a little bit. The time that it took to cut those cores varied a lot, especially, well, it got better once we got faster at it, but can everyone see my screen again? Are we good? Okay, I'm not seeing any comments, so all right. Yeah, if it was if there wasn't very much sediment in the ice, then it was pretty quick to drill, maybe just a minute or two. But if there was a lot of sediment, it would take like what felt like 10 minutes. It felt like a long time to drill these out, but we got better at it, and we had a pretty good system. This was us drilling a clear block, as you can see. So, yeah. All right, alternative projects. So after we developed our ice core drill, we learned there was an article that came out about a drill like this with threads on the outside. And this basically is called a chipmunk drill. So the threads are on the outside, so it allows the ice excavation easier, and then you have a core on the inside. So yeah, for the next project, we'll hopefully do something like that. All right, pros and cons of our method. Cost was pretty cheap. It was less than $1,000. A little bit of time to figure out how it works, but that's research. The materials were readily available, so all the steel we got at Metal Supermarket or what we had in the shop. We can choose any ice core diameter. So if we wanted cylinders that were 6 inches wide, 6 inches diameter, then we could do that. And we used a battery powered drill, so that makes it easier. We don't have to plug it in. Cons. There was a lot more specimen prep, as you can see from the picture. With the chipmunk drill, they just drill straight into the ice. Ours, we had to cut it down and make it fit in the template. Ours also required a walk-in freezer because we did have to cut it down. So I spent last summer in the freezer, which was kind of fun. And there was a little bit longer setup time. Yep. All right, some of our lessons learned. I've kind of mentioned this, but having a place for the chips or shavings to evacuate was crucial, because otherwise the saw would get stuck and then it would start melting the ice and then kind of freeze in place. So didn't work very well. We added the second inner hole saw blade on the inside to provide an inner gap between the core drill wall and the ice, so it reduced friction and prevented it from the ice core from breaking off. The steel tube was machined with a lathe to keep it as to ensure that it was a true round tube. And I kind of mentioned this earlier, but our second iteration didn't work as well because it was a thinner tube and we weren't able to get it down to true. And then we would also try to have a more effective use of steel products available if possible. So our prototype, which is our first version, we had a 3.5-inch diameter tube, and then we machined it down. So we have our hole saw, which is the dark blue. The tube originally was the big circle, and then we machined it down so it aligned with the hole saw. So the big circle is the uncut tube, and then machined down to line up with the outside of the hole saw. And then we have the saw OD and the saw ID. So we got everything to line up. Like I said, we did try a different one, but the measurements ended up not working with the products available. And so it wasn't round true enough. So we would recommend a little bit different size tubes next time, or different size samples. All right, so now I'm going to switch over to talking about shear beams. So remember, you have compression on the front and shear basically on the edge of the pile on the side. So the left side is kind of your before view with your ice coming toward, and then this is kind of your after on the right. So you're putting forces past each other, and that's the shear beam breaking. And then the top one is the front view. So you have a skinnier block, and it's the forces are actually going through the long or the wide face to provide a shear surface. So yeah, the failure face is tangential to the pile. Yep. All right, so this is some pictures of us cutting the shear beams. We use the chainsaw to get a square side and or this bandsaw that we put in the freezer, and then cut them down. We made a jig and worked pretty well. So the one on the left and the bottom are the clear shear beams we cut, and then the top right are some of the samples from the port, and you can see significant difference between the layers of the ice. So there's way less sediment on the right side than on the left side. So we built basically an environmental chamber to test these. So we have our MTS machine on the right, and then our insulated homemade environmental chamber. And then we hook that up to a freezer that goes to -70 degrees Celsius. And I believe when we were testing, we set it to -40 degrees Celsius so that the testing chamber would be about -10 Celsius when we were testing. So for the compression testing, we made these compression platens. So basically they have aluminum outer rings and polyurethane core. And basically it just allows a place for the ice core to sit so that it doesn't like slide out. And so the ring confines so it doesn't slide out. And it's also the polyurethane is soft, so it reduces localized stresses at the ends. And that basically just allows the ice to, it's more likely with the polyurethane, it's more likely to break in the center instead of at the ends, which is not ideal for what we're trying to find out. So this is what the compression testing setup looked like. One of our platens was fixed and one of them was compressing. And then we had our platens at the top and the bottom of the ice sample. And then we had our ice sample on the inside. So our target strain rate was 0.001 inches per second. And then to determine our loading rate, we multiplied our target strain rate times the height. So if we had a cylinder that was 8 inches tall, our loading rate was 0.008 inches per second. Yep. And we also took pictures of all the samples before and after, if we could, if they were still like in place after, and kind of looking at like failure lines. Can't think of the right word, but kind of like with concrete, you can look at see where the failure was, and yeah. All right, so this is the testing apparatus for the shear. So if you look at the center or right hand picture, you can see that there are 4 points. So the center 2 is where the load basically was applied, and they're going past each other because they're shearing. And then the 2 outside were just to help stabilize the beam. Yeah, so on the right, this is one of our beams beforehand. And we put, the rubber bands are holding thin little pieces of carbon fiber to reduce denting into the ice during testing, because that can impact how it breaks and the shear strength. So yeah, and then the right shows the shear force diagram. So you're trying to break it between the 2 bars here in the center, like the center region basically. And then this diagram also shows the bending moment diagram. So the 2 left pictures show some of the failures. The middle one shows the port ice specimen failure, and most of them looked like what the port specimen looked like. So they would break in the middle, either into 2 pieces or 3 pieces, but 3 pieces was more common. And then the left one shows one of the shear specimens, and this one broke outside of between the 2 bars, which we didn't see very much of, but it shows, it was cool with the clear ones because we could actually see it like cracking while it was going, versus the port ice. You could not tell that at all because of all the sediment. And our loading rate was 2.5 millimeters per minute. So, all right, so data, we had lots of data. We had 111 compression tests and 34 shear tests from the port ice. From the clear ice, we had 6 good samples of compression testing and 5 shear tests. So our average compression strength was 582 psi, and that was our average maximum. Yes, I can show which part of the, okay, so question, oops, go back. Can you show which parts of the testing apparatus are moving during the test? Yes, so the bottom was fixed and then the top was pushing down. So it's, this was actually, the top plate was actually on a swivel, so we could line it up correctly. And there's actually a counterweight up here, this little orange thing right here, because this would kind of lopside to the plate when we were testing. So we would lower it down so it touched, and then make sure it's like perfectly aligned. And then we added a preload of about 10 pounds, and then we would test it. Good question, thank you. Oops, too far. Okay, So our average maximum compression strength was 582 psi with a standard deviation of 122 psi. And then our average maximum shear strength was 169 psi with a standard deviation of about 40 psi. And then this graph on the right shows pretty close to your stress strain diagram, not quite because it's load versus stress, but we have our displacement on the x-axis and our load in the y-axis. So we have, pretty close to elastic strain leading up to the failure, and then there was a little bit of plastic deformation after. And then this shows a bunch of different stuff. So pile 1, that's just location of the pile. But the elevation was at the bottom of the pile. So all the blue ones are samples from that pile. And then same thing with the black and gray. Those are the P1 middle. So that's basically all from one block. And then red and orange is from the P2 bottom block. And then same thing for the other block. So we could compare, okay, all these samples are from the same block. They're all, radial or transverse, and we can see how similar they were. All right, so a comparison of parameters. So we had our average compression strength versus our direction. So remember how I talked about, we have our radial. I actually have my my fake ice block here. Forgot about this earlier, but so when we cut it out, we would cut out the shear beams, and then this is our radial cylinder. This is our center on the front. Our radial cylinder looks like this on the side, and then we have our transverse cylinder going in from the side, and then our vertical cylinder going in from the top. So those are our directions. So this graph on the left compares the strength in the different directions. And then we've got our N is our number of samples. So it looks like the radial is a little bit weaker than both the transverse and radial cylinders are weaker than the transverse and vertical ice cores. And then this graph on the right is actually pretty similar, but we also included whether they were in the shade or the sun. So shady or sunny orientation. So there's a bit of a mix. For the radial, the shadier samples were weaker, but in the transverse and vertical direction, the shadier samples were stronger than the sunny samples. So it doesn't really tell you, it tells you something, but it's not a significant, notation. It's not significant. All right, so pretty much so earlier I mentioned we compared all these things. So we compared strength, stiffness, elevation, salinity, the amount of sediment, the depth, like how far from the radius, and I'm forgetting one more, but we compared all these factors, and there was basically only one factor and between two parameters that was relevant, and it was this one. So it was the compression strength versus the depth. So the cylinders on the ice cores on the outside layers of, the ice cores on the outside layers of the ice with respect to the pile were stronger than the ice cores closer to the pile. So that's kind of interesting. All right, this graph on the right looks at the compressive strength versus the stiffness. And the stiffness, so we had a power equation here, relationship here, I believe. So yeah, as it's getting stronger, it's also stiffer, which makes sense. All right, so this is our comparison to clear ice. And on the left, we have clear ice versus strength, and the clear ice is stronger, which is true. Fresh water is stronger than briny water. And then we also compared the density, and the clear ice density was much more dense than the port ice, which also makes sense when you think about, or when you look at the strength versus between the port ice and the clear ice. All right, so this is a comparison of parameters for the shear. On the left, the x-axis doesn't really have anything, but the vertical has the shear strength. So our 2020 ice, oops, wrong direction. Our 2020 ice is significantly weaker. And this is only because it was sitting in the freezer for 1.5 years instead of just a couple months between like when it was harvested and when it was tested. And when I noticed that, at the time I was taking ice engineering, and I realized that grain size plays into that. And so for future, we'll have to think about, okay, we have the samples and we'll try to get them tested as soon as possible. So this year we harvested the ice or did field extraction in February and March, and then we ended up testing all the samples over the summer. But the 2020 ice was sitting in the freezer for 1.5 years instead of just 5 or 6 months. And so that played into why it was weaker. And then this just shows the different strengths of all of our shear samples. So it's about between 150 and about 225 or 220 psi for shear strength. And then we also compared the shear strength with the shear stiffness. And again, you have a positive relationship. This one's linear, but not a super strong relationship with an R squared of only about 0.3. So yeah. Oops. Again, we compared the port ice with the clear ice. And again, the clear ice was stronger than the port ice in shear, and it was denser than the port ice. So. All right, so our ice parameter correlation conclusions. There's a nonlinear relationship between our compression stiffness and strength. There is a linear relationship between our shear stiffness and strength. There's no relationship between the compression strength and shear strength. And then there's a correlation between the strength of the radial distance in the pile, but it's not a very strong one. And there's no correlation between strength and the compass direction, or like whether it was in the sun or the shade, the salinity, the elevation, or the amount of sediment. So there was actually less stuff, like less correlations than we kind of expected, which was interesting. So this is the design parameters for the Port of Alaska new project. Basically, the most important thing to note here is the ice compressive strength. This is the ice flow compressive strength, which is 300 psi. And we'll note that in a minute. I'll be doing some calculations from the engineering ice manual to figure out, how strong the ice is in Cook Inlet and the ice forces on the individual piers, and then kind of comparing that to the ice that our experimental data, and then also using that for the modeling, kind of as a three-way check. So for the modeling, we'll be developing an ice-ice structure interaction finite element model to simulate the ice impact. So pretty much similar to what you see in the picture here, but we're gonna do it 2D from basically looking top down. I'll be using Abacus, and I'll be assuming 2D plane stress. So the first thing I'm gonna do, or I'm doing right now, is creating the compression and shear models, or the tests. So I'm gonna, have a cylinder that's compression testing, and then a shear beam that's shear testing, and then comparing those to their experimental values we got and adjusting the model as needed. And then we're gonna simulate the pile conditions, basically what you see on the right, but in 2D. So yeah, the next steps, of the project is build the model, and then we're working on the characterization of ice. So we're having, from this graph from earlier, we have, linear elastic ice properties until the failure, and then after that we have plasticity material properties, and we're looking at the concrete smeared cracking model, see how that compares, and go from there. All right, so some conclusions from the ice core drilling. We determined that the most important thing was to have a place for the ice shavings to evacuate. And then I mentioned this before, but the average max compression strength is 582 plus or minus 122 psi. And as I mentioned, there's some small variations in the directions between the radial, tangential, and vertical directions. And then there's one significant correlation, which is the depth versus compressive strength. And then for the average shear stress, that is 169 plus or minus 40 psi. And then this kind of brings me back to what I talked about at the beginning. So if the sheet ice compression, which is 300 psi per the design criteria for the project, is stronger than the accreted ice shear, which I just determined based on our data is 169 psi, then the image on the right is what we can assume. So basically the accreted ice is breaking off and the pile diameter is crushing the sheet ice, which is also shown in the picture at the bottom right. So that's kind of what we determined from our data. All right, lots of thank yous for this project. ConocoPhillips Alaska, Port of Anchorage, Great Lake Tree Service, Loken Crane Company, Corbin Rowe, our machinist, Tim Kirk, who's the lab manager, and set up all the testing for me, and then Dr. Tom Ravens. And then I also have a whole slew of undergraduates to thank: Haley Swerball, John Morton, JC Van de Hey, Keelan McKinnon, who spent the whole summer in the freezer with me, John Scott, Sean Carlson, and Levi Purdy up at UAF helped me with the Python coding. So thanks Levi for that. All right, any questions?
All right, thanks, Jasmine. I'm actually involved. I'm actually required to ask the first question of you because there's a delay in the live stream. So my question is: the new port expansion project has new piles going in, and those are actually 12 feet, I believe, in diameter instead of 3 feet in diameter. And so, not to put you too much on the spot, but can you speculate based on sort of your introductory problem statement what the effect of a much larger pile diameter would be? Does that make sense?
Yeah, the larger the pile, the more ice force it has to resist. So it's going to have to be significantly stronger to accommodate that. There could be an argument that the wider it is, the more space there is for the force to be distributed and absorbed. But I think that, the wider it is, the more force is going to be applied. So it's going to have to be stronger.
What about the accreted ice?
There's probably going to be way less accreted ice. So you only have to account for, so the accreted ice on the sides, which if we're talking about shear strength, there's going to be probably less accreted ice in terms of a ratio between the pile width and the accreted ice. So you don't have to increase the design parameters or it's less, the amount that you have to increase the pile strength is less in terms of a ratio between what's existing now and that. Does that make any sense?
Yeah, no, that makes sense. You'll have the ice will be a smaller percentage of the overall width of the pile.
Yeah.
All right, so here's another question. Did you look at corrosion at all with this project?
No, we did not.
That's right. um, did you, I guess we didn't go down there in the summer. Do you, uh, yeah, so there's a lot of other people doing a lot of work on the fact that a lot of these piles are heavily corroded. Um, so that has all kinds of seismic implications. But there has actually been some speculation that the ice is helping um, the corroded piles to kind of be stronger in the winter, which is a different direction than we were going, but it's definitely something. That's now that we know more about the ice, we could actually, you know, figure out if the ice is actually helping or not. So, um, you concluded that the accreted ice is weaker than the sheet ice, but none of the pictures show accreted ice shearing off the piles by sheet ice. Thoughts on why that might be?
Yeah, so I'm gonna log out or go back to my first picture. So this is the side closer to shore. So all the boats are, all the ships are parking on the outside. And so the only interactions that the ice on the piles, the accreted ice is having here is just with this floating ice every time the tide goes up and down. So if this was, an oil platform in the middle of Cook Inlet, then there probably would be more ice or less accreted ice on it because there's ice flows hitting it more frequently and kind of scraping it off. But since there's not a lot of flow back here and not a lot of movement, especially since the tide's going up and down instead of just consistent flow, there's not much breakdown in the accreted ice.
Did you actually conclude that the accreted ice is weaker than the sheet ice?
Yeah, so the shear strength of the ice that we determined was about 170 psi.
Okay.
And the design requirements this is the design requirement compared to the design requirements by HDR for the port project. They're expecting that the ice flows have 300 psi of force, compression force.
Okay. I think the other thing to point out with that question is that the design event that Jasmine's talking about is exceedingly rare, right? The idea that a actual piece of sheet ice floats in and hits the port, like we don't really have pictures of that period because it just doesn't really happen much. So, and then of course, it might happen at 2 o'clock in the morning when nobody's out there. It's actually really hard to get pictures of the ship side of the port, like the part that's over there on the left, the far left, right? Like you can't just take a rowboat out. They don't like that, right? Okay, another question. This is a good question. Any thoughts on how you change or modify pile design after your research?
To be honest, I haven't really thought that far ahead, but I'm gonna try to answer for you. So if we know that the accreted ice is going to break off when the ice flow hits, then we can kind of reduce the pile size because as soon as that ice breaks off, then your pile diameter decreases, and so it doesn't have to combat as much compressive force. So obviously this would have to be tested way more and way more research into it, but I think eventually we could get to the point where we know exactly how strong this ice is, especially with more research and the Northwest Passage opening up and this becoming, a more common problem. We can, once we have more information, we can maybe reduce the pile size. And of course, there still needs to be factors of safety, and it's going to change, port to port. But that would be kind of cool to, have some more definite numbers, maybe reduce pile sizes and save some money.
Yeah. Would you increase the pile diameter like to 12 feet, or?
I think that's an interesting solution, but I haven't really heard of that before you asked me that question. So I have to think about it a little bit.
All right. Another question is, there's a lot of piles that have jackets on them. How did you take that into account?
I didn't. I don't know.
Well, let me put that question in another way, and you can answer. So, the pile jackets. My recollection from the photos and what I've seen, I have not been involved in the actual jacketing, but typically the jackets, they'll put something like, a half-inch thick steel sleeve around the existing pile. So the question is, would increasing the pile diameter by half an inch on each side affect, your research?
Yeah, I mean, my understanding is that the pile jackets are placed on the most corroded ones, so it's kind of like making up for like not damaged piles, but weaker piles. And so, the stronger the pile, the more it can withstand. But in terms of like the ice strength, which is what I was specifically looking at, it doesn't really impact it so much. When I do the calcs in the like ice forces, that will definitely play into it, but I haven't quite gotten there yet.
Okay. And then of course, adding an inch of diameter to a 3-foot pile is not really going to change anything, right? Okay, last question, which is, and this is a good non-structural question. Does the accreted ice also increase the water velocity loading?
Accreted ice also increase water.
Right, so if you are designing a pile, you design it for currents.
Because it has more surface area to go around.
Yeah, hitting it. So the question is, does that also increase your water velocity loading?
It would make sense to me that it does, because it has to go around it, so it increases the velocity. Just like in a river, the water's moving faster around the bends than in the straight sections. But
so yeah, that would increase the water velocity, but also the loading, because it's wider. So just at the same velocity, it's basically the same argument as the floating ice, right?
Yeah.
Although I would venture that the water velocity loading, I haven't done this math, but I would assume it's probably very small compared to the impact loading from a sheet of ice, for the current that we're talking about. But that's speculation. I don't know if that's true.
Yeah, I can pretty much only speculate.
Call a water guy. I don't know. All right. Well, thank you, Jasmine. That was really informative, and obviously there's a lot more work to be done now that there's better procedures for doing and testing ice. So many of you are interested in your PDH hour. So the way that you get that is you go to our website, which is really easy to find. You can just Google UAA Professional Development Seminar, and it will show the list of all the speakers, and down at the bottom there's a link or an image for the YouTube live stream, and then just to the right of it there is an image that says Qualtrics, and it's got a big Q. You click on that, and then the passcode is vertical, all lowercase, VERT, however you spell vertical, TICAL. And so yep, you just type in vertical, and then it will ask you your name, etc., and you can directly print out your PDH certificate, a PDF of it, and that's it. So again, the passcode is vertical, and I will also note from that list that this is the last seminar of the semester for us. So thanks to all of our presenters and everybody for tuning in this semester. We will resume again in the fall, so sometime like last year. I think the first one was sort of mid-September, and you know, same time, same place. Maybe, hopefully, next fall we will be in person again. For those of you not here, the campus has become unlocked again, and we are all pseudo interacting normally. Classes are back to normal next fall, so hopefully we will all be able to see you and provide refreshments for lunch on Friday back here at EIB. So with that, I think that's everything. So thanks, Jasmine, and thank you all for joining us.